Now this is another interesting distribution in probability, that is Poisson distribution. When lambda is any positive real number and a random variable x which is having a range 0, 1, 2, 3, so on up to infinity. Now the interesting fact for Poisson distribution is, so far both the binomial distribution and the standard probability distributions are defined only when the random variable's range is a finite number, right? But here Poisson distribution is helpful when the random variable's range becomes a countably infinite set. When the range is an infinite set having values 1, 0, 1, 2, 3, so on up to infinity, then the variable x is said to have a Poisson distribution if the success of R probability is given by e power minus lambda into lambda to the power of R by R factorial. Now to understand this, do you remember what is expansion for e to the power of lambda? Yes, it would be lambda to the power of 0 by 0 factorial plus lambda to the power of 1 by 1 factorial plus lambda square by 2 factorial plus lambda cube by 3 factorial, so on up to infinite terms, which is in short denoted in sigma notation as sigma r equal to 0 to infinity lambda to the power of r by r factorial is the value for e to the power of lambda. Now, considering a very trivial fact, e to the power of lambda into e to the power of minus lambda will always become 1, right? So, can we rewrite this as e to the power of minus lambda into the expansion of e power lambda, which is lambda to the power of 0 by 0 factorial plus lambda to the power of 1 by 1 factorial plus lambda square by 2 factorial, so on up to infinite terms is 1. Now expand this term with e power minus lambda on each side. Then this is e power minus lambda into lambda to the power of 0 by 0 factorial plus e to the power of minus lambda into lambda to the power of 1 by 1 factorial plus e to the power of minus lambda into lambda square by 2 factorial plus so on up to infinite terms, where the general term can be expressed as e power minus lambda into lambda to the power of r by r factorial is 1. Now if we take this general term which we obtained, that is e to the power of minus lambda into lambda to the power of r by r factorial, look at each of the term, all of them are positive and sum of an infinite positive terms is 1. That means each of the term on the left hand side strictly less than 1. Then when we consider the term e to the power of minus lambda into lambda to the power of r by r factorial as probability of the random variable x taking the value r, then the notation which we marked here can be expressed as a sigma notation as sigma r equal to 0 to infinity p of x equal to r, right? And this happens to be 1. So now what do we observe here? Sum of infinite random distributions probabilities is giving us 1, and each of them is a positive quantity which is between 0 and 1. Therefore, the event x equal to r takes a probability of e to the power of minus lambda into lambda to the power of r by r factorial. Such a distribution obtained is called Poisson distribution, right? Let's apply this Poisson distribution to very simple problems. If a random variable x follows Poisson distribution with parameter lambda, then the mean of x and the variance of x is lambda, that is same as that of the parameter in the Poisson distribution. So let's prove this idea with a parameter not printed here. It's going to be lambda. So what does Poisson distribution give us? Yes, p of random variable x equal to r is given by e to the power of minus lambda into lambda to the power of r by r factorial, where r can take the values ranging from 0, 1, 2 up to infinite, right? So let us calculate the mean first. By definition, what is mean of a distribution? Mean is sigma r equal to 0 to infinity, because here we have the random variable taking infinite values. Yes, r into probability of x equal to r, that is sigma r equal to 0 to infinity r times what is probability of x equal to r by Poisson variable. It is e to the power of minus lambda into lambda to the power of r by r factorial. Can we rewrite these terms as sigma r running from 0 to infinity r into e to the power of minus lambda into lambda to the power of r minus 1 into lambda by the denominator r factorial we will express it as r times r minus 1 factorial. Now the excess r gets cancelled and the term which is unaffected by sigma we will put it outside, that is lambda comes outside. Look at the term which is inside the expression now. R runs from 1 to infinity, e to the power of minus lambda into lambda to the power of r minus 1 by r minus 1 factorial. Now what is this value? Summation of all the individual probabilities, that would be 1. So this is lambda times e to the power of minus lambda into e to the power of lambda, which gives us 1. So what is the mean obtained? Yes, the mean obtained is lambda. So the parameter of the Poisson distribution itself will be the mean of the probability distribution. Now in the case of Poisson distribution, let's evaluate the variance of the distribution. Let us consider the variance as rho square. Then let's consider rho square plus mean square is sigma. What is rho square by definition? Variance. Yes, it is sigma r equal to 0 to infinity r square into p of x equal to r. That would be sigma r is 0 to infinity. This r square we will try to express it as r times r minus 1. So an excess minus r has been created, so that we will add up and compensate, times what is p of x equal to r by Poisson distribution? Yes, it is e to the power of minus lambda into lambda to the power of r by r factorial. So let us split the terms with respect to the bracket here. Then the first term would be sigma r is from 0 to infinity. As there is a term of r minus 1, we'll start the summation from r equal to 1, r into r minus 1 into e to the power of minus lambda into lambda to the power of r by r factorial, plus the second sigma for the second term of the bracket starts from sigma r equal to 0 to infinity r into e to the power of minus lambda into lambda to the power of r by r factorial. Now clearly you can see the second term is nothing but sigma r into probability of x equal to r. So this second term is nothing but the mean of the distribution. So the first term, when we simplify, r into r minus 1 can be cancelled in r factorial by r minus 2 factorial times, right? So rewriting the first term, e power minus lambda is unaffected by the summation. So we'll rewrite this as e to the power of minus lambda outside, sigma. Now r is 2 to infinity. Because denominator has an r minus 2 factorial, let's not start with a negative factorial term. So we start r value with 2. So it is numerator is e to the power of minus lambda taken out. Can we express this as lambda square into lambda to the power of r minus 2 by r minus 2 factorial, plus what is this value? This is the mean of the Poisson distribution, which just now we observed to be lambda. Now look at this term, lambda square is unaffected by summation. So that also will come out along with e to the power of minus lambda. So e to the power of minus lambda into lambda square times sigma r is from 2 to infinity lambda to the power of r minus 2 by r minus 2 factorial plus lambda. Now do you recollect what is this term inside sigma? Yes, this is e to the power of lambda itself. So what is this value? E to the power of minus lambda into lambda square into e to the power of lambda plus lambda, wherein e power lambda into e power minus lambda is 1. So this is coming to be lambda square plus lambda. What we calculated is variance plus mean square, and it is coming to be lambda square plus lambda. So can we write variance plus mean square, that is lambda square, is lambda square plus lambda. So when we remove these terms, what are we left with? The variance of Poisson distribution, that is rho square, is also the parameter of the Poisson distribution, which is lambda. So if you observe this, in theoretical, when the random variable can take infinite possibilities, then the mean and the variance of the distribution would be same. Both of them will be same as the parameter lambda of the Poisson distribution. So mean is lambda as well as the variance is also lambda. Let's try to understand this Poisson distribution through very simple problems. If x follows Poisson distribution such that probability of x equal to 1 is same as 3 times the probability of x equal to 2, then find the variance of x. So let us consider the variance as the parameter of the Poisson distribution. So this lambda is nothing but the parameter of Poisson distribution. Then What is the condition given? Probability of x equal to 1 is same as 3 times the probability of x equal to 2. Let's recollect what is Poisson distribution. So probability of x equal to r variable. Yes, the random variable x equal to r will happen with a probability of e to the power of minus lambda into lambda to the power of r by r factorial. Now, can we write the value of p of x equal to 1 and p of x equal to 2 by this definition? Yes. What would be the value? P of x equal to 1 is e to the power of minus lambda into lambda to the power of 1 by 1 factorial. This is given to be 3 times. What is probability of x equal to 2? E to the power of minus lambda into lambda square by 2 factorial. E to the power of minus lambda cancels on both sides. So we can cancel 1 lambda on either of the sides, which gives us lambda equal to 2 factorial by 3, that is 2 by 3. This 2 by 3 is the parameter of the Poisson distribution, but as we need variance, the variance of the distribution is also same as lambda, which is 2 by 3. So even if the mean is required, mean is also same as that of the parameter of the Poisson distribution. Therefore, for the given problem, the variance as well as the mean are both equal to the parameter, which is 2 by 3, right? Now, in a city, 10 accidents take place in a span of 50 days. Assuming that the number of accidents follow the Poisson distribution, find the probability that there will be 3 or more accidents in a day. So look at this. Let's create the parameter of the distribution. That lambda, which is the parameter of Poisson distribution, is same as the mean of the distribution. So mean in general by statistics is the average of, so first let us calculate the average accidents per day. Yes, what is the data given? There are 10 accidents that takes place in a span of 50 days. So on an average, how many accidents happen per day? It is 10 by 50, which is 1 by 5. Now this 1 by 5, which is the average accidents, as average is similar to that of mean, is playing the role of parameter of Poisson distribution, right? So we have lambda value. Now what is the requirement here? Let x denote, the random variable denote the number of accidents per day. So the required probability is probability of, what is the random experiment which denotes 3 or more accidents? Yes, x greater than or equal to 3 is the requirement. As the Poisson distribution is defined on an infinite set of range of random variables, it's more convenient if we express this as 1 minus of, yes, what are the complement events of this? Probability of x equal to 0 plus probability of x equal to 1 plus probability of x equal to 2, right? These are the 3 events which do not satisfy this. That's why we wrote it as 1 minus of probability of the 3 complementary events. That is 1 minus of, yes, by Poisson distribution, what is p of x equal to 0? E to the power of minus lambda into lambda to the power of 0 by 0 factorial plus e to the power of minus lambda into x equal to 1. So it is lambda to the power of 1 by 1 factorial plus e to the power of minus lambda into lambda power 2 by 2 factorial. We know the value of lambda, so let's replace the values. It is 1 minus of, yes, e to the power of minus 1 by 5 into lambda to the power of 0, 1 by 0 factorial 1 plus e to the power of minus 1 by 5 times lambda is 1 by 5 by 1 factorial is 1 plus e to the power of minus 1 by 5 into lambda square is 1 by 25 into 1 by 2 factorial, that is 1 by 2, which is, when simplified, we can take out e to the power of minus 1 by 5 common. So this becomes 61 by 50 times e to the power of 1 by 5. This is the probability of there will be 3 or more accidents in a day, right?